Good afternoon. This is Gary from last time and yesterday. So we talked about sources and nodes and things like that. So we start now to get to know several components that we will be using throughout the module. First one is the very basic component. Resistors. The resistance of a resistor is given by R, which is equal to rho L over A. Rho is the resistivity, L is the length of the resistor, and A is the cross-sectional area. Now in that aspect, if you take a cube that has that side length of 1 meter, the resistance of opposite sides to opposite failures is the resistivity, because L becomes 1, A becomes 1, that is 1 meter square. So the resistance across the two opposite phases is the resistivity. Right? Now you can see, if you want to increase the resistance value, you either need to take a material that has a higher resistivity, or you need to take a longer length, or you need to reduce the cross-sectional area. Now these diagrams or photos show different types of resistors. The unit of resistance is ohms. The unit ohms is the name of the scientist. So it is capital O. Notation is capital Omega. There are two main types of resistors. One is the fixed resistor, the other one is the variable resistor. Fixed resistors, two main types of course there are three: carbon film resistors, metal film resistors, and wire wound resistors. Then you have variable resistors. Now carbon film or metal film resistors, these two are, this side you can see carbon, and this is usually metal film. Now how they are built in that is, they take a cylinder, ceramic cylinder, small ceramic cylinder, and they coat the outside of that cylinder with a thin layer of carbon. Right? And then, then if you measure the resistance in the end, two ends, that would be the cross-sectional area, will be the cross-sectional area of the skin, the carbon skin, and the length would be the length of that. Right? So the resistance would be less value because you have a larger cross-sectional area, right? And length is short. So what they do is they create a spiral on this, spiral shape on this. So the length is large. So it becomes actually a carbon spiral. Right? Carbon. Same thing for the metal film as well. They coat the outer or the surface of the cylinder with a metallic coating and then scrape a spiral on it. So by adjusting the thickness of the coating and the width of the spiral, the scraping depth and things like that, you can adjust the cross-sectional area and the length, and thereby you can adjust the resistance. Can you adjust the resistivity in there? No, because it is carbonated. Right? So the only two parameters that you can adjust is the length of the carbon strip and the width of the and the depth. So the cross-sectional area. So by doing all these stuff, you can create a thick wire. And ultimately, what they do is they put two metal caps to which the lead wires are connected. So that is what you can see on either side as two plugs. Right? Anyone who has broken a resistance seen inside. Okay, today in the afternoon when you go home, you buy few resistors and break them up and bring them to the next tutorial class. Right? Buy few, spend. Now you are usually spending hundreds of rupees for your snacks and things like that. So it's okay to spend 100 rupees and buy large number of resistors and break it. Right? Different size, like large resistors are there, small resistors are there. Right? Then the other type is, I'll skip this for the moment. The wire wound is wire wound. The only difference is that they take a wire, metal wire, and they wind it around the similar similar rod, like ceramic rod, right? Now, if you compare this metal film or carbon film together with this wire wound, now when you create that spiral, if you scrape it, you scrape the skin that is already made, there are defects in there, right? Defects in the thickness, the edges, and when you scrape it, there are certain, there can be chips coming out of it and so on and so forth. So the errors are more compared with the wire wound. Now wires can be precisely drawn, right? Then it's a wire, and even you can measure the exact resistance, right? And then wind. So the accuracy of wire wound resistance, the valid accuracy is high. However, because it's metal, you can have lower resistance. Carbon, well, there are two forms of carbon. One, we electronic people love. The other, females love. What are the two types? What do we like? What do we love to use? And what do they, the females, like? Which male would hate? Because you have to spend everything in your pocket and buy that for females. What are they? Yes? The two forms of carbon, not chemistry, right? General knowledge. Diamond, which is what we hate and females love, and graphite, what we love and females might hate, right? So we don't bother about diamond because diamond is a very rigid material, no electrons at all, so there can't be any conduction, right? That is why it is with that much pressures, right? Whereas carbon, the graphite has sp2 hybridization. If you can recall your chemistry knowledge from your A levels, which you might have totally forgotten after by the time of the A level examination, right? sp2 hybridization, where one electron per carbon atom is actually free in a cloud. So that electron would help us to travel some charges, right? Transport some charges. So that is graphite. So graphite is what is used in this device, carbon resistance. Excuse me, I am not having good health today. Right, so variable resistors, you have different types of variable resistors. The principle is the same. Principle is this. They have a sort of rotating part, which is the center point, sliding on top of a carbon film again, right? So by changing the position, if you rotate that slide towards this end, the resistance between the middle and the right would be lowered, and the middle and the left would be increased. Same way, if you rotate the other way around, left hand two terminals would have a lower resistance, and the right hand two terminals would have a larger resistance. The resistance between these two would be fixed because it is a carbon strip. Right? Similarly, you have the other alternative of the sliding, the variables resistors, the linear orientation. In the linear orientation, we have some arrangement like this. You have the carbon strip, straight line or linear, and you have a metal strip as well, and the sliding mechanism is like this. This is the slide, right? So this end and this end gives you the fixed two ends, and this will be the variable point, right? You see this linear type in these graphic equalizers, sometimes in amplifiers for volume control purposes, right? The other one is the rotating type, which is available in most of the electronic devices for volume controlling purposes and so on and so forth. Now, on the other hand, there are different sizes of these, like small size one, which are usually called as presets. Preset. So that is there for the purpose of adjusting the value before you use the device. For adjustive purposes, initial adjustive purposes, that is why it is called as preset. You set it priorly, after that during usage you don't do anything. Right? That is not robust as the other one. So that is the purpose. Construction is the same, but construction hardness, reliability, robustness are different. Right? That is the purpose of the first type, the smaller one is for adjust once and keep it there. Right? But the other one, and for example, the volume control. Would you satisfy with a single volume all the time? No. Maybe 100 times per day you change the volume by channel or whatever it is, you change it. Right? So for that you need something that can be altered very often. Right? So that by construction that gives that feature. Other than that, the construction, I mean the internal operation is same. The next type is thermally sensitive resistor. We call it as thermistor, where the resistance of the device changes with temperature. By the way, I forgot to mention these are the two symbols: fixed resistor, variable resistor. Sometimes the variable resistors can look like this, sometimes like this, or even like this. Right? All these are variable resistors, and this terminal, or the one that was there in the slide, is this. This terminal, this one is the varying component. These are the two ends of the the carbon strip, right? And the thermistors, temperature dependent or temperature sensitive resistors, we got two different types: positive temperature coefficient and negative temperature coefficient. So the variation of resistor with temperature is positive in PTC, positive temperature coefficient, and it is negative in negative temperature coefficient. And you can see that these two curves I have drawn not as straight lines. They are not straight lines actually. Right? The relationship is not linear. Right? It is a curve. The details are given in the data sheets. So they are used for temperature sensing purposes. Right? Maybe for fire alarms and things like that. Right? So if you have a higher temperature, it will give you a lower resistance or a higher resistance. So it can be used as a temperature sensor. Continuously, these devices do have them. Right? So that is that. Then we have the light dependent resistance, LDRs, where the resistance of the device changes depending on the light falling on the cell. Higher the amount of light falling, the lower the resistance is. The lower the amount of light falling, the higher the resistance is. Different LDRs do have different different maximum resistance values and different minimum resistance values. So you have to find out what the range in the application that you are using it. The symbols are given in here. Right? We went through this. Alright. The resistor values, standard resistor values. Now you can't find any resistor, like for an example in a calculation you got 101.25 as the resistance value. Will you be able to find it? No. Right? So you will have to stick to the practical values that are available. Now, each way E6, E12, 24, 48 and so on are there. Out of those, these two are almost not available in the market. But we got E12 series and E24 series. E12 series, there are 12 different numerals, there are 12 different values in the decade. Count it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 10 is 10 to the power 1 of 10. 1. 10 to the power 1 of 1. So that is, this is actually the starting point of the next decade. Right? So the values are 1, 1.2, 1.5, 1.8, 2.2, 2.7, 3.3, 3.9, 4.7, 5.6, 6.8, 8.2 and that's it. Right? Now did I look at that? No. So next time you should be able to read the numbers, write the numbers without looking at the board. Because if you are given a bulk of resistance, which they will be giving in the lab, and ask you to find out 10k resistor, right? You can't go through all these stuff and find it. Or else you are in the process of developing or deciding something, finding doing a calculation and trying to finding a resistor that would suit that place. Right? Say the calculation became 102. You should know in a flash, okay, I can select 100 ohm resistor in there. Right? Now, so here you can see the different values that are available in the different ranges, right? For your reference, you don't have to remember, you can't remember actually all this stuff, right? But the key range, which is highest available range in the market, is E12 series, right? So that is what I showed in here, right? Now the tolerances. Certain accuracies are allowed in the particular value ranges. Now what is allowed by E12 series is 10% tolerance. So that device can have 10% error, maximum of 10% error, right? Whereas E24 allows 5% only, it doesn't allow 10% error. Let's see why. Now in the same way, if the error is 20% for E12 series, that is a problem because the maximum error that is allowed is 10%. Let's see why is it so. Now let's take an example. 100 ohms, right? 100 ohms plus minus 10% means plus minus 10 ohms, right? So this can be between 110 ohms and 90 ohms. The one below this is 82 ohms, the value, right? In E12 series, the next lower side value is 82. Higher side value is 120 ohms. So now you can see that these edges does not overlap with the next adjacent values. That is a requirement. Now if this had 20% error, plus minus 20% error, then it would be from 80 ohms to 120 ohms. Now you can see 80 is less than this, 120 is larger than this, equal to it, which is an overlap, which is not possible, right? So that is why they say, okay, with E12 series you can have a tolerance of 10% maximum. You can't have more error than that. But what about 5%? Can we have 5%? Is it an issue? 20% we saw that it is not possible. What about 5%? 5% is okay, right? If it is 5% error, it's better accuracy, lower error, right? 5% error, if it is 5% plus minus 5% error, it will be from 95 to 105, which is well away from this and this. So the range is narrower than the original specified range. So 5% tolerance is okay for the equivalent. Similarly, if you go back to this so similarly, now E24 series 2% tolerance is okay, 5% is what is recommended, but 2%, 1% tolerances if they are there, it's okay. But 10% tolerance for E24 is not recommended, right? So that is, now most available series is actually E12 series with 5% tolerance nowadays. But rarely or seldomly, randomly, you might be able to find E24 series as well, right? Now you can see, if you look at this one, another thing, I'll come into that little later on. The color code, right? The resistor color code. Now the color code has 3 different variants: 4 band, 5 band, 6 band. 4 band, you have 4 colors. Usually one color is printed little away from the other thing, so that you have to keep in the right portion, which is the tolerance band, which gives you the tolerance of the resistor. Now why do we need tolerance? Because the manufacturing process is not ideal, right? Keep in mind, this is the practical world, nothing is ideal, right? You boys would expect a girl like Aishwarya Rai, but you will never get it. You females, girls would expect a boy like Hrithik Roshan, but you would never get it. So this is a practical world. So although we say 100 ohms, it is not exactly 100 ohms. If they say 5% tolerance is there, the value can be between 95 and 105. Any value we don't know, right? Now even if it is for a single batch, now this is a single batch. Are you identical to each other? No. So likewise, in a single batch of resistors, they will give 100 ohms, let's say, different resistors. If you take 2 resistors, they might have 2 different values, right? So that you have to keep in mind. Now that is where this tolerance band is triggered, right? So we know, okay, this is our accuracy. The value can be, although it is treated as 100, it can be from 95 to 105. Any value between those. It can't be beyond lower than 95 or beyond 105. That's for sure, right? So now how do we read it? Let's take an example. Brown, green, red, gold. First 2 you write as it is. Brown, oops, that is brown, right? Brown is 1. I will let you look at this later on. Brown is 1, green is 5. You write those 2 numbers as it is. The third number, so this comes there, this goes there. 10 to the power, red is 2. Plus minus gold is 5%. Right? This is how you write. First color as it is, second color the number as it is, third color 10 to the power of that number, right? Now The other 5 band. 5 band, first 3 numbers goes as it is. 4th is the multiplier. 5th is the tolerance. Right? So you can see that in here. Now if you look at this again, the this one, up to E24, last digit is a 0. So which means you have only 2 numbers. But 48, you see 100, 105. That means that you need 3 numbers to represent the value. Right? So you need 5 band color code. Right? And then the next one is the 6 band color code. It is similar to the 5 band, but you have an additional color, 6th color, which gives you the temperature coefficient. Temperature coefficient is how much resistance gauge would be there per degree Celsius change. Now it says, I believe you have good eyesight. I can see, although I am old, 100 parts per million, 50 parts per million, 15 parts per million, 24 parts per million. Now what does that mean? Parts per million. For those who are familiar with the chemistry, would have remembered. Now in here, what is a part? Resistance unit. Ohms. Right? So what does it mean by 100 parts per million? In simple words, per 1 degree change in the temperature, there will be 100 ohms difference in the resistance value if the original resistance value is 1 million ohms. That is what is meant by 100 parts per million. 100 ohms difference per 1 million ohms per degree. Right? So that is what is meant. Increase in temperature will reduce the resistance. Reducing temperatures will increase the resistance. So 1 degree increase in temperature will reduce the resistance by 100 parts per million. These are needed for military applications and space applications. The military applications, there is a huge temperature changes, like when you are launching weapons and things like that. Space applications also, whatever the temperature that you are working here is not the temperature that is in the moon or the space station. Right? Huge difference is there. Even aeronautical applications, aircraft applications, you undergo a huge temperature variation every flight. Right? When you go up there to the 11,000 feet, the temperature goes to several tens of negative degrees. Right? So if you work with the current temperature, room temperature 24, 26, 30 degrees, will be trouble. The estimation will be wrong. So for that, you need to know the accuracy based on the temperature as well. Now, well, did you know any technique or any method that you have used? You might have used to memorize this color code. We had a sort of coin. Right? Kalu dua, run family card kotak, nil dam kalu tu dua. Right? Black, brown, kalu, dua. Right? Kalu dua, run family, ratu family, card kotak kaha kola, nil dam kalu tu dua. Right? So anyhow, you have to remember this. Right? Among little things that you need to remember. Well, remembering and practicing are two different things. So you have to keep practicing. Right? You have to be practicing this. Right? So black, brown, red, green, yellow. Sorry, red, yellow, green, blue, purple, gray, white. Did I read it correct? So later on, when you be familiar with resistors, you just make in a flash you will be able to read the resistor, right? So we will do that exercise in the tutorial, right? That in a flash you read a value. Let's do that later on. Capacitors. Capacitors are made by sandwiching. How many of you eat sandwiches? What do you sandwich in between the two slices? Right? So sandwiching a dielectric in here, not a slice of cheese or anything else, but a dielectric, right? Which is an insulator, right? You sandwich an insulator in between two metal plates, right? Sandwich and insulator, which you can see here, a dielectric between two metal plates. The unit of measurement is farads, the gauge name, so capital F, and the notation is capital F. The capacitance C is epsilon A over D. Epsilon is the dielectric constant or permeability of the dielectric or the dielectric constant of the material in between. And A is the cross-sectional area, D is the distance between the two plates. Right? Now, I want a large value of capacitance to be built. What can you do? How can you build that? From that equation, by looking at the equation. What can you do? One option is increasing the dielectric constant. Right? Now, dielectric constant is a property of a material. If you take wood, it will have a particular dielectric constant. If you take paper, it will have another. Ceramic, another. Polythene, another. Right? So you can't actually select whatever the dielectric constant that you want to have. But you have to stick to the dielectric constant of the material that you use. Right? The other option is you can increase the cross-sectional area. Larger the cross-sectional area, so you bring this big capacitor, so it will have a large capacitance value. But you can't put that in your computer, right? Or a power supply. Now the small power supplies that you can buy from the market, so usually got 1000 or 2200 microfarads capacitors in them, right? So can you make this big capacitor and put it in there? No. Then it is not portable, right? You will have to take it in your backpack, right? So there is a restriction there, right? And the other is the distance between the two plates, which is actually the thickness of the medium in between, the layer in between. Now, ceramic has a very high dielectric constant. However, can you roll? You can't roll ceramic into a very thin layer, right? You can make a very thin layer, very thin in the sense micrometer range, from polythene, paper. But both these materials, polythene and paper, got much lower dielectric constant compared to the silicon. Now an issue, right? You got a good material, but you can't make a very thin layer out of it. You can make thin layers out of certain other materials where you don't have any, much better or better dielectric constants. Now problem, right? You compromise one feature to get another feature. Now how do you overcome that? People have, the one option is like paper, polythene, you can roll it so that actually effective volume or the size is smaller. But still the volume remains unchanged, right? You can't roll 1 meter of sheet into very small capacitor, right? You can't. So what you have to do is to use some other technique, right? This shows actually a ceramic capacitor. You can see the two plates, and one of the plates you can see here, and this is that red color is the ceramic layer. Grade 1 ceramic capacitance, see what is there. Right, the issue is ceramic is not flexible. So you have to make it into a disc. Right, then you can't roll it. Right, so see, different restrictions or limitations are there. You have ceramic which is having a very high dielectric tensor compared to paper, polythene, everything, but you can't roll it. You have to make it just like a disc. Right? You make it a disc means your cross section remains extremely small. When you roll it, you can roll maybe a few inches into a smaller tube, like ceramic. The other option they have found is they found that there are certain salt solutions, electrolytic solutions, when you put them, let's say I'm exaggerating the situation here, the two plates are there, this is a thin paper blotted with the electrolytic solution. You know what is known as an electrolytic solution? A solution that has ions in it. A salt solution, anions and cations are there. When you apply a proper when you apply a proper voltage onto these two, it creates a very thin oxide layer of the material, the electrolyte. That oxide is a very good dielectric or very good insulator. Right? And what about this thickness? Now this is a sheet of paper. Right, and dielectrics, I mean the salt solution, oxide layers, few oxide layers are it's in the nanometer range, because molecules are in the angstroms range, 10 to the power minus 10, right? Few maybe tens of those layers will give you maybe say 1 to 2 nanometer thickness, which is never be achievable by rolling or stretching or what it is. Right, so stretching, rolling, none of those mechanisms you will be able to roll it to a nanometer scale. But this oxide build up is just in nanometer range. So in that case, two properties, epsilon A over D. Let's assume that A is not changed. Epsilon is much higher. It's a property of the oxide. You select the material such that that oxide gives you a very good dielectric, and the thickness between the two plates is also much smaller. So what will you get then? A very large capacitance, right, for the same size. So the electrolytic capacitors, however, need a correct potential to be applied across, right? That is why they actually have, if you can see here, a mark. This mark shows that side is your negative, this mark shows that side is your negative, and this arrow shows that this side is your negative. So you have to apply the right potential like voltage to get the capacitance happening. Right? Capacitance working. If you suffer on the voltages, it will not work. Right? So different types of capacitors are there. You can see different numbering patterns are there. These and supercapacitors are there. You can carefully go through. Now these capacitors, you can see that they are the number, voltage, everything is clearly printed because they are large, right? But these ceramic capacitors and so on, they are very small, so you can't. They usually don't print the number value, but they print the number code. Right? Let's look at that little later on. Before that, the variable capacitors, what they do is they take you two semicircles, semicircular plates, and let one be stationary and one be rotating. So effectively, when you rotate it, the cross-sectional area underneath or between them changes from 0 to the full cross-sectional area. In between, good olden days, the wireless wireless radios, the wireless, right? They used to call it as wireless, right? They had this, not even this small, like this big tuning condensers, variable capacitors. Right? So they were air cooled. The material in between was air. Right? Because it is air has a very lower dielectric constant. You need to have a larger number of parallel plates to build the required capacitor. What was the thing? Was there princess in your dream? Prince in your dream? A king riding on a horse? But later on, they have found this very irritative material, the polythene. Good uses are there, but it is generally a very bad material for the environment. Polythene had a much better dielectric constant, right? And when you put it in between the two middle plates, the capacitance is much higher than when you have air, right? So that way they could miniaturize the size from this, like something like 2-3 square cubic meters into 2-3 cubic centimeters, right? And these are again like presets. They are there for initial adjustment purposes. Not that robust, not as robust as this. Principle is the same, but by construction, this is there only for initial adjustments. Adjust it. But this is for peculiar adjustments like the tuning in radios, right? Channel tuning in radios. You use this variable capacitance. Now the number coding. Number coding for capacitors. Again 3 numbers like the 3 colors. First number as it is, second number as it is, third number is the 10 to the power value. Value is 20 picofarads. Right? The last, you have a letter. Right? That letter gives you the precision or the tolerance. J for 5 plus minus 5%, K for plus minus 10%. We go back. Okay. There this is 2 to 1 J. 102 J. So what is 2 to 1? 2 to 1 J. 220 picofarads plus minus 5%. You don't have to take a photo. It's there in the poster. So 102. 102. 1000. That is 1000 picofarads. J is plus minus 5%. Right? So this actually shows that the electrolytic capacitor, the oxide layer is very thin and dielectric is actually conductive. Salt solutions are conductive, right? So you can treat actually the other side of the oxide layer as the second metal plate, not the actual physical plate, right? So that is why the D becomes very small. So all this stuff can be considered as conductive. So this surface becomes the other plate, right? Okay. End of capacitors. Now inductors. Inductors are coils, right? Any wound coil would have an inductor, self-inductor. We will be talking about inductors later on as well. Here we just get an introduction to inductors, but details of inductors will be there in the latter part of the module. There can be different materials in between or inside: air, iron, or ferrite. Air core, iron core, ferrite core. Different types can be there. Either you buy an inductor, or you can buy inductors that are wound around ferrite cores, right? They are really available to people. This you can label the inductors value in millihenry or what it is, but here you can't. So they have a color code. Later on we will look at the color code. This is a ferrite core. This is also a ferrite core. These are air core. Now the value is the unit is Henry, which is a very large unit. So millihenry, microhenry are the inductors that you will find. So the inductance value is given by n squared, which is the number of turns. N is the number of turns. That squared. Mu is the permeability, which is the magnetic constant of the material in between, right? And A is the cross-sectional area, L is the length of the inductor, total length of the inductor. So larger the permeability, the larger the inductor is. Air, I said air core, iron core, ferrite core. Air has the largest, smallest permeability. Iron, the next. Ferrite, the highest. Right? So that is why in the small inductors you have a ferrite rod around which the coil is formed. Right? But this is very small, so you will actually get very small inductors from those. If you want a large inductor, you will have to buy it. Right? Millihenries, of course, you will have to buy it. They are bulky. Right? The large bulky inductors are in the millihenries range. Right? Similar color code is there. Same way you read it, 3 color bands. But the value you read is in microhenries. Same technique, so I am not going to go into detail. Same color code. Same number of colors, same values, but the value you read in resistors it was in ohms, but this is in microhenry. Now, if you see something like this, would it be a resistor or an inductor? Would it be a resistor or an inductor? How can you distinguish? Of course, by looking at outside, because there are most of the resistors, of course, have the yellow background, but there are resistors that are having blue background. So, if you have a blue background, resistor is blue background, and inductor is blue background, you will be in trouble. So, what you have to do is you have to read this, right? Check if it is, check with a multimeter, ohm meter, if the resistance is equal to that ohms. If it is not, this is an inductor. Right? That's the only way that we can find it out. Maybe looks alike because it has the same construction. You have the white green and then the blue cap, right? So it is like. Well, inductors are a little bit blurry than the resistors, but that's a weak metal, right? You have to be sure that you are putting a resistor or an inductor. Otherwise, the person would be electrical. The person who is using would become electrical, right? So, let us say that's all. Right? Transformers are used to reduce or increase voltage. So again, there are two windings instead of single winding like in an inductor. We will be talking about transformers later on in the subject in the module, later part of the module. We can have air core, iron core, and ferrite core again. The voltage ratio of the primary winding, primary is input side, secondary is the output side. Primary winding is the ratio, voltage ratio is proportional to the turns ratio. Right? Relay is an electromechanical switch. We talked about single pole, double throw switches mechanically controlled. This is an electrically controlled. You have an electromagnet onto which the attraction would be there of that lever, right? So you can use them as switches, electrically controlled switches. You may have only normally open contacts or normally closed contacts, or both, or multiple numbers. Some number of normally open, some number of normally closed, but it is. Sometimes there will be single pole, single throw switches inside. Sometimes there may be single pole, double throw switches. It depends completely on whether you put a probe or not. The mechanism would switch, but if you don't have a contact the other side, right, you don't have any electrical conduction going, right? Circuit symbols, some we have already discussed, some we will be learning later on. We just put for completion, but what is more important is actually this part in this, in that symbol set. Circuit connections. There are two basic standards. One is this one, the other is this. First standard, you denote a junction or joint by a dot and a cross by not putting a dot. Right? The second standard is you denote a cross by drawing that jump symbol to clearly show that there is no connection between the two wires, in which case you don't draw a dot for a joint. There are people who uses the hybrid version. People tend to use hybrid, right? This and this for more safety, right? More readable, right? There are no mistakes. You clearly show a joint by a dot. You clearly show a cross by the hoxie, right? Which is much safer than using any of these two standards alone, right? So some books, some material, you would see this together with this. You never use this together with this, okay? Right? So you have to use one of those. Either this, or this, or this and this, but not this and this. Right? It has to be the two better ends, right? Dot for the joint, cross or off signal for the cross. Right. Block diagram. Circuit representations. Now, can you tell me the operation of this circuit? What is illustrated in the slide? Can you explain what it is? Yes or no? Yeah, sorry. Can you explain? Is it possible? Now you don't know any electronics, right? Except you hobbits were there, the others don't know electronics. Right? You don't know electrical. Right? But can you explain this? What is illustrated in this diagram? It has a microphone enabled. Yes. You don't know what a microphone is, but it is a microphone. Right? So there is a microphone. There is an amplification system which amplifies the signal, and the output is given to the speaker, which releases the sound waves. You can see that what is accepted by the circuit is a sound wave, and what is given out is also a sound wave. In between you have an amplifier, power amplifier, and a power supply. Right? The signal goes to the amplifier and then the power amplifier, which are both powered by the power supply. So any person who can read a diagram can explain this. But if I am giving this diagram to you and ask you to build this circuit, will you be able to build it? Unless otherwise you are given the amplifier block and power amplifier block and the power supply block, you won't be able to do anything. Right? I give you a set of components, right? Resistors, transistors, capacitors, and so on and so forth, right? And then ask you to build this circuit. Will you be able to? No. This is used at initial stages usually for presentation purposes to describe the basic operation of whatever you are proposing. If it is a design, you brainstorm and say, okay, we need this unit to be there. We need that unit to be there. We don't know how to build that, but you can write down all strict parameters. Right? Now let's take for an example. We want an amplifier to amplify the signal of this form. You can specify. We want this many watts to be there at the output, right? And we want the signal to be picked up or taken out from the microphone or headphone jack from the phone, right? And we can propose, okay, it to be working at using 5 volts, so you can use a phone charger for that, right? All those specifications can be given and put it into a block diagram, right? And this, anyone who has referred to Vijay newspaper would have seen, right? So this is there for kids, those who actually don't know what's in here, right? Here you can see that there is a battery, and battery looks like a battery, a pictorial diagram. Switch looks like a switch. So if you are given these two items and ask maybe a grade 5 kid to assemble it, he would have it. Right? But now you are undergraduate students, so we will not be using this sort of diagrams, but we will be using these diagrams those are known as schematic diagrams. So every component is depicted or represented by a schematic symbol. A battery, switch, and a resistance, or battery, switch, and a lamp. So from this you should be able to identify that, okay, what we are going to assemble is something like this. Right? Now in the beginning, I know there are some people who might have not even thought of electronics, electrical, right? Or some people maybe they are who are even afraid to turn on a switch, right? Plug in a device, that is it, right? So at the beginning of this module, or whenever you feel like you need in the lab classes, we will not be giving you this sort of a diagram, but we will be giving this sort of diagrams, schematic diagrams. But before you come to the lab, if you are not familiar, if you don't feel comfortable just by looking at this to assemble the circuit in the lab, your freedom is there to draw it in whatever the way that you want to draw it in your lab. Right? And if you feel like you won't be able to assemble this within few minutes or maybe few seconds, preferably, right, within a minute or so, or maybe couple of minutes, right? But if you feel like you will need more than that much in the lab class to assemble this circuit, you better draw it in a pictorial diagram, including the breadboard connections, right? So that it is straightforward for you to assemble the circuit with the laptop. Right? That's for your own benefit. Right? But we will not be giving any sort of circuit diagrams like this. Right. Then prototyping. I said at the beginning yesterday that we will be building a circuit throughout the lab series. Right? Step by step, you build it and you will be taking it home. Right? Taking it to the next semester's module as well, the program. Right? So for that, we need to know a little bit about prototyping. Electronic prototyping. Now prototyping is not manufacturing. We don't try to build the product, but we try to build the concept. Sample. Right? So different sequences are there. First of all, like you draw the block diagram and you brainstorm, you discuss with the others and put down everything that you would need into a paper. Right? Let's say I want a device to give a beep every time someone is following me. Because that can be a bit poker. Right? So that's my requirement. Now you put down all the requirements and features that you would need. I need a beep, I need a light, I need a vibration, right? I want it to be chargeable, right? And if the charging level or battery level is low, I need a different alarm. All those stuff put into concept. Then proof of concept. You come up with different circuit techniques, right, to solve the problem that you have laid down. Right? Well, within this year, you will not be traveling through all these stuff, right? We'll be giving you the problem, right? But you will be doing certain parts of it. But for completion, I have put all this stuff. This is the entire process that you will have to go if you are actually developing a circuit. And this might help you in your DLC, design and process. Right? So there are two modules, first semester, second semester, where you have to come up with a project. Right? So this is how you should go. Right? Then device development. So once you find out different techniques to solve different things, you put them together, right? And then you simulate, assemble it, verify the application, you build few pieces, right? First one and test if it is basically working, and then you manufacture a pilot batch, right? Because always it will not give you the perfect product at once. So you manufacture few, maybe 10 pieces, 100 pieces, and let people use it, let people test it. Test patterns have to be there. Test scenarios have to be there. And then once everything is confirmed and tuned up, you go for mass scale production. Right? So in that, we'll be talking about few things. So the initial design is what we are talking about here, not the manufacturing. Right? So initial design, we have first design the concept or come up with the concept and then put down blocks into that and then simulate. Why do you simulate? Before you try to build up the first prototype, you see if it is working. Sometimes you calculate some errors, right? And a little error maybe, right? That can cause more fire explosions in the circuit. To avoid that, what you do is you simulate and see if the current levels and things like that, current voltages and things like that are accepted. Even after that, then it can burst, right? Do something wrong, it can burst. But this is a safer sequence. For simulation, you have different types of software. Time domain software and frequency domain software. Time domain software, once you assemble it, turn the switch on, in the simulator, you can see that if it is a light circuit, you can see the lights are going on, off, and so on and so on. This time domain might not be now two of the software, Multisim and Proteus. Proteus is very close to real time, meaning that something that should happen in 1 second would happen approximately in 1. But in Multisim it is slower, the execution is slower. Sometimes it may take 3-4 seconds for something that should happen in 1 second, but it's still in time domain. Now if an LED is there, it should blink. You can see that the LED is blinking, but slower. Right? If a waveform is there, you can see that the waveform, the voltage is increasing, decreasing, and so on and so on. So it's time. Frequency domain is waveguide is wide. You let you assemble a circuit and you simulate it. You can say, okay, this is the frequency spectrum and things like this. You can't see any real time or time domain happenings in a frequency domain analysis, a frequency domain simulation. There are situations like in amplifiers, you want to know what are the frequencies that can be amplified by the amplifier and so on and so forth. In that case, you use frequency domain. We will be using Multisim, and Android apps are also there. I found this very useful, Electric Circuit Studio. So while you are on the right, right, you can test your circuits. Right, you can test it for operation. You can test like all these theorems that we are using, all the circuits that we are working with in this module can be tested. Time domain as well as transient. Transient is if you turn on the signal, what would happen during turning on? That is transient. Right, you have a circuit, all of a sudden you switch on the input. You make the input from 0 to let's say 5 volts. What would happen to the output? That is the transient. That is also available through this small app. And with that, all of you have smartphones, I guess. Right? You can put that on and play it. So left hand side you can see the Multisim interface. On the right hand side you can see the interface of the Electric Circuit Studio. And this is the voltage divider, which we will be talking about in too. Right? Two resistors in series works as a voltage divider, and you can see what is happening in there. Right? Right. Prototyping. Electronic prototyping. There are different types which got some of their own advantages as well as disadvantages. Right? We'll look at some of those. So there is breadboard which we will be using in the class, right, at the early stages to test your circuits. Plug and play, right, easily assemble, right, customizable, right. You have internal connections in this. We will be talking about details throughout the lab classes. So you plug the components, you can make connections to using jump wires and things like that, and get it going. Disadvantages are there because they have parallel plates inside to make the connections. They have capacitance effects, inductance effects, and so on and so on. Those connections can be there. So all those issues are there. But it is a very good method for initial testing. Right? You have few components to be assembled and checked if it is working. Right? You connect them. If the breadboard is good, you have the lab. Right? So particularly for lab applications, lab testing, right, laboratory work, this is the idea. Because every time you walk into the lab, new group, you'll have to assemble the circuit again and test it, and before leaving, you have to remove it. Disassemble it and keep the breadboard separately and components separate. The components separate. Right? The next is the springboard, which is actually sort of obsolete one, but it has its own benefits. Similar to the breadboard, but instead of metal strips under it, they have springs. So higher currents can be thrown and the connections are firm. What you do is you pull apart the spring and put the connection there. So when the spring compresses, that makes the connection. So higher currents can be drawn using spring boards. Then you have this wire wrap. People been using this as permanent technique, right? So you put all the current components into some support like a weather board or so, and you make all the connections by wrapping a wire and connecting the other end to the other component, right? Which actually is beneficial because you can make the circuit without much delay, and large currents can be drawn, but the drawbacks are that diagnosing is not that easy, right? Because it's like a mess, right? But if you do it carefully, that is a permanent technique. I mean, a technique that is used for permanent applications as well, right? Whereas breadboard is not, right? Breadboard, springboard are not permanent solutions. They are for temporary testing purposes, but this is not a temporary testing purpose. This is for permanent application. The next is the perf board and solder. You have a board full of holes, so you can insert the components, but nothing other than that. So you need wires, routing, soldering to build a circuit, right? Perf. Different variations can be there. In this one, you don't have any connectors, but you have pads, right? Circular pads are there, so you can solder the components onto the pads first before you make the rest of the connection, right? So this is more firm than this one, because here you don't have a pad. Instead, you just have to solder component to component. But here you can solder the components to the pads, like you can see here. Right here you can see that you soldered it. Even in these places you could have they could have soldered into the pad. Now these things are available in two different tip sizes. One is 100 mil, which is 1/10 of an inch, right? The other is larger than that. I can't remember how much it is, right? Exactly. But the first one, like I said, 100 mils exactly suits the gap between two IC pins, VIP packet, 1/10 of an inch. The other larger one is for transistors. So the pin gap of larger transistors is larger than this much. So the other board, now if you are buying one, you have to be very careful. Different sizes are there. You can't plug in an IC into the larger one. So you have to be careful. Then generate printed circuit boards. We call these as strip boards. This as dot board. This as strip board. They are generic. They have certain copper strips already laid. So in this case, if you want to make connections, the strips are already there. But don't forget that the strip from one end to the other end is connected. So if you don't want that much distance, you will have to just damage in between. Damage the strip in between, then you want this connection. Oops. Right, so now you will be using this as well. Right, in the evolution, first you will design it, you will test piece by piece, and then you will assemble it, the whole circuit in a breadboard and test it. Then you will be assembling it on a strip board or a dot board and test it, solder it, right? Then you will be designing a PCB, that is this one, right? PCB. Right? Final would be a PCB, and thereafter that will be for assessment. Ultimately, we will try our best. Coronavirus has affected us, not for our physical health, but we were planning to import the high quality PCBs per each person. We'll have to delay it. Let's see, maybe by next semester, right? But within this semester, you will be building your own circuit. But the moment that we could get them down, we will give you the PCB, so you can solder your own circuit in good quality. And then take it to the next module, which is engineering programming. So the ugly board or dead bug. Ugly board, because this looks ugly, right? Dead bug is because all the components are upside down, like a dead bug, a dead cockroach, right? So, however, this is actually a very firm technique that people use for permanent circuits as well. But one-off. If you need one or two boards, rather than going for a PCB, you just do it like this. One main benefit is there, you put everything on a copper board, which is a good shield, right? And which is a good support. You can hold all the negative terminals or all the terminals that need to go to the negative onto the copper strip, which is made the ground. Right? So it is very firm, soldered, but it doesn't look nice. Right? Ugly. It got its own benefits, disadvantages as well. Then the PCBs. PCBs are very handy when you want to manufacture hundreds and thousands of the same circuit. Right? Duplicatability is there. Once everything is finalized, you let a PCB manufacturer to manufacture it. Right? Thousands, larger the number, the lower the prices. Right? So, and identical circuitry would be there. Just a matter of soldering the components, the layout would be identical to each other. Right? So, that makes the life much easier in mass scale manufacturing. And also, the previous technique that we were talking about, you can't use surface mount devices. And also, you can't have multi-layers in the circuit. But in PCBs, they have developed techniques to have multiple layers, sometimes 3-4 layers in between. Right? There is usually, like motherboards and so on, usually use one of the layers for power, one of the layers for ground. So shading techniques can be there, and you can print any detail. Most of the time, there are situations where you print antennas, inductors on the PCB routings themselves. Right? The antenna is a wire. To route it in the required shape, the small Wi-Fi devices, small Bluetooth devices, they all have the antenna printed on the board itself. Right? All these flexibilities are there with PCB. Mostly, it is repeatable. Once the design is finalized, even if it is manufactured in China, just a matter of asking them to print some 1,000 more copies. Right? They will do it for you. So this is a sample. So you can have silk screen. This green shield is known as this is for protection purposes, so you don't put drop solder on those areas. And the other side you can have the seal screen where you print all the details like the component numbers and things like that. So all those facilities are there in PCB. And they look nice. Right? They look much nice. Now if you make a PCB, it may look ugly. But if you get it manufactured, right, from a good company, they look nice. Right, next, SIUs. To finish off the discussion for today. And few more slides are there. Few minutes around 20. Right? Still stands. Yes, SIUs to one and all, but I have high activity. right? So basic units, then mass, time, electric current, temperature. They are measured with the SI units, meters, kilograms. Note that this is not grams but it is kilograms, right? Seconds, amperes and kelvins. So the SI unit for temperature is not Celsius or Fahrenheit, it is Kelvin. And the derived units, for example, force, Newton, is kg ms minus 2. Right? So they are derived units. You can have it. And unit conversions, empirical to SI and vice versa, Fahrenheit to Celsius, both to Kelvin and whatever. How many of you have scientific calculus with you? Everyone must have. Right? If you are doing engineering, you must have a scientific calculator. Right? So, scientific calculators would have, or they have, these unit conversions. Right? Unit conversions are there. So we are not giving you any unit conversions in the paper. You need to use the calculator for that. Go home and refer to the manual and find out where the unit conversions are there. Also the constants, scientific constants, the charge of an electron, Coulomb, everything are there. Constants, right? Charge of an electron, Kelvin constant, right? Boltzmann constant, all are there stored in the calculator. So you will have to use calculators from next week onwards. Right? So the next class, next tutorial class, you have to bring your calculators. Right? Because we are not giving you in A levels, this is in A levels local, we used to use log tables, right? Right? So here now onwards we are not going to use log tables, otherwise we will be using, you need 10 hours to do that, to our paper. Lot of calculations are there, right? So all those calculations you will have to use the calculators. Now you better start using calculators now, right? Now again another source from the matrix. Can you remember the same? Those who have watched the matrix, those who downloaded the matrix last night? Oh, okay. Right? When Morpheus was training, fighting for the first time on the training platform with Neo. Those who have watched the matrix? Can you remember that scene? Right? Morpheus says, stop trying to hit me but hit me. Can you remember? The Neo was giving a hard time or giving a good try to hit Morpheus, but he could not hit. So Morpheus says, stop trying to hit me but hit me. Likewise, what will happen to you is, you will try to use the calculator in the examination if you are not using, if you are not used to use the calculator. So stop trying to use the calculator but use the calculator in the examination. Right? What is the difference? Trying to use it, you try to use it but you can't get the maximum order. Right? But if you try to use it now, you might fail, but you learn, and then in a flash, you do it correctly. You have to do it fast and you have to do it correctly. There are tricks and tips by using calculator, like result carry forward and things like that. Right? So you start using calculators, particularly for the people who have done London local levels. London level you will be using it. Yeah. Local levels, no, you didn't use. You used that big book, the log books. Right? So for multiplication you have to touch your ear like this, not even like this, right? So you convert the two values into logarithm values and then you add them and then you convert that back into the, right? So what's the hell? But we are removing that hell from you by giving you a calculator, you giving you the opportunity to use the calculator. And as a result, we are not giving much weight on the calculations in the examination. Right? right? But your values have to be correct. Why? How many are planning to do civil engineering? Okay. Let's assume their calculations are wrong and the beam size of this is much smaller. Can't handle the weight of this class and everything collapses. We all die. Right? So that is why your calculations have to be accurate. Right? Those who are doing electrical and electronic engineering? Okay. So if you do a calculation wrong in a ECG machine, the machine will, the doctors are so stupid, right? They only know what is said by the medical reps, right? And what is there in the book. If the signal is this, you do it. Right? These days they use these few medicines: cetirizine, loratadine, piriton. What else? Antibiotics. Right? They kill you. Right? They kill you, basically. If you have a cold, you don't have to use antibiotics. Why? Now, you know, for ages, for decades, now you are, yes, you are 18 years old, so a couple of decades, right? You've been sort of cheating your immunity system. Am I right? Because there are advertisements saying that you have to use Dettol, right? Antibiotic soaps, right? Yeah, Lifebuoy, Dettol, right? What they do, they gradually kill you. They gradually ruin your immunity system. Sometime down the line, you will give birth to your own kids. Don't let them use Dettol or any antibacterial hand washes. Why? Now for an example, if you don't know how to swim, or people who are around rivers, around the sea, they naturally start learning swimming. You don't have to jump into a pool. Right? Likewise, if you are around bacteria, our system is starting fighting with them. You are capable enough to fight with them. Your system is trained to attack them. But can you remember what has happened to Prince Siddhartha? Right? That's an advice. So the king Suddhodana wanted to hide everything from him, the nature. That people get sick, people die. He has hidden everything. And what has happened? All of a sudden when he saw everything, right? He got frustrated. But if he got to know that from small age, my teeth don't leave the wife and the kids. Right? So it's the same thing that might be happen to you. If you don't train your immunity system, you are not capable of fighting. Your body is not capable of fighting. Right? So let your body be trained. Likewise, you have to train before you go to the examination. Right? So what I was talking about is electronics. You design the ECG machine wrong, so the doctors, they are so stupid. Right? I'm repeating that. Right? And they are so heartless. You have seen that previous days in news. Right? So you don't be like that. You be helpful to the people, right, and helpful to the country. Right? Okay, you are paying for the course, but don't mind, help the country, serve the country. Right? They learn from us, and they are against us when we need actually their help. Right? So shall we start? I actually don't go to doctors very often. Right? There are doctors, by looking at your face, they prescribe antibiotics. whereas you don't need it. Right? Antibiotics are needed if, okay, what happens here really is, when there is a virus attack, your body gets weaker. As a secondary attack, there can be a bacterial infection. If that is there, then you need an antibiotic. But better if you use something like a medicine, herbal medicine that increases the immunity. Right? That will help you a lot. For the one, for strong. Right? That will help you to increase your, not burn you. Right? That will not kill you, but that will attack the virus from your body itself. None of these medicines are killing the virus, but the antibiotics are killing the bacteria. It will kill you as well, causing you and the bacteria. Right? But any herbal medicine would not do that. That will trigger you, your immune system, so that it is actually your immune system attacking that, not the medicine. Now the doctors will feel like, okay, according to this ECG, you are having a hole in your heart, whereas there is nothing like that. Because your calculations with your resistor values were wrong, your amplification configuration was wrong, and the ECG signal was so big, or whatever it is, that they will recognize. And now they will say, okay, you need a surgery that will cost you, I think, 22 million rupees. And there is a huge list in the government hospitals, so you will have to do it urgently. Right? That is what they will say. Right? And without any issue, they will undergo, they will do an open heart surgery for you. Right? So you don't have any issue. Mechanical engineers, those who are going to do mechanical engineering, you can raise your hand for anything. Where is it? Okay, I'll come there. Mechanical engineering, okay. You do a great design of braking system of a car, where all of a sudden when you are driving at 100 kilometers per hour, you need to apply the brake. When you apply the brake at fullest possibility of higher power, and the car doesn't stop and it goes and kicks. Right? So that's what happened. A disaster. Right? So that is the material. I'll give you a funny example. You decided marvelous material, and in the test run it's a dress. You bend, it tears off. That can happen. Right? And material is companies are materials. Right? Although it is in undersea build, it's material. You design a bridge with wrong materials. The material engineer produces the material that is said to be of the required standard, but it is not. Can take down. If this ceiling comes down, all of you will be in trouble, including me. Right? And materials engineering, aircraft material, heavy strength, lightweight. Material engineers design those. Material engineers design Titanic. And well, wrong calculations. They didn't think of the extreme cold temperatures. That's what happened. They thought, okay, even with extreme cold temperatures, the steel would have its own properties, But what has happened is it became brittle. So material engineers have to be responsible for that. Right? They didn't think that. See, your calculations are extremely important. As I said in my inauguration speech, we are dangerous than doctors. Right? Doctors can, maybe they put us to a pair of scissors inside your body, and so, right, only one person would die, right? But if a civil engineer does something wrong, if we do I'm an electronic engineer, right? And if electronic engineers does something wrong, an aircraft can collapse because the communication, signaling and things like that in landing and taking off, we take care of them. If a single inch difference, it goes, right? So we are more dangerous, and that is why we will be penalizing you for wrong calculations, but we will not be giving more concentration on the time that you spend for calculations, because you do it with the calculator, right? So we don't give much time, but we give much weight. If you have wrong answers, we will be penalizing you, right? Okay, now there is of course, and more than that, what is important is the engineering prefixes. The powers of 10 we are interested, that is 10 to the powers of 3. Kilo, mega, giga, tera, milli, micro, nano, pico. Right, 10 to the power 3, 6, 9, 12. I think peta is also there, that is 15. Downside, it's not P double TA with peta, that more than peta, but PETA, if I am not mistaken, 10 to the power 15. Right, meaning 10 to the power minus 3, minus 6, minus 12, and minus 9 and minus 12. So those are the engineering prefixes that we prefer to have. Right? Right. The last topic for today discussion, significant digits. Now, let's take these examples. If something is measured as 3.57, it's a measurement. We know that it is its accuracy is for 1 centimeter, a meter rule, right? A meter rule. 3.57 is 3 meters 57 centimeters. Meter rulers usually have 1 centimeter difference. We don't know anything beyond that. But a foot ruler has 1 millimeter. Right? When you don't have millimeters on the ruler, we don't know whether it is 1 millimeter, 10 millimeter or so. We know only up to 10 millimeters, 1 centimeter, 10 millimeters. So this means that it is close to 3.57, but it is not closer to 3.56 or to 5.8. That's the only information that we have. We don't know what is happening with the next digit after 7. We don't know. Here, if we say it is 3.570, that has a completely different meaning. That means that the value is closer to 3.570 than it is to 571 and 569. So the accuracy is now larger. Now, you should never write 3.57 if it is the measurement as 3.570. Right? 3.57 means that you actually know up to that level. You don't know the next decimal place. Particularly in our case, we will be using multimeters, digital multimeters. The multimeters you can read maybe it's usually 1888. Right? 4 digits, the most significant digit is only a 1. Right? So in that case, your numbers would be only 4. You can't read anything beyond that. You can't go to accuracy of 5 numbers, 6 numbers, no. Only 4 different numbers can be read. Right? So significant digits is the number of digits, say meaningful digits in a number. So in this case it is 3. Right? And in this case it is 4. However, this example 0.00457 can be represented as 4.57 into 10 to the power 3. So therefore you have only 3 significant digits. Right? Only 3 significant digits. All these are not significant. The zeros that are there on the left hand side are not significant. Right? Now what is the importance of this? If A is 3.76, B is 3.7, what is A into B? Multiply that and see. 13.912 is the, if it is exact. Right? If it is exact, 13.912. That is, if this number is exactly this much and this is exactly this much, it is. But we know that they are measurements. If they are measurements, we have a tolerance, plus minus last digit. Right? So the value can range from this to this range for the A, this range for B, resulting in the result range from 13.50 to 14 point something. So in such a case, as a rule of thumb, what we do is, when you multiply or divide, the result must have the lowest number of significant digits of the original numbers. Now in this case, first number has 3 significant digits and second number has 2. So the lowest is 2, the result should have only 2 significant digits. Right? So in that case, it is 14 because the result is 13.912. 2 significant digits means 2 non-decimal places, so you round it. Not round up, but round off. Now what is the difference? Round up, round down and round off. Round up means we always round to the upper side, round down, round to the lower side. Rounding means whatever the closest. Right? So this is 14. It is not 14.0. If you say 14.0, you have 3 significant digits. Right? It is 14. That's it. Right? That is for multiplication and division. Addition and subtraction. Now let's take this example. 24.7 amperes. So 3 digits read from the multimeter. You don't know what is there on the after 7. You don't know. That can be 0.1, 1, 2, 3, 4 up to 9. Right? And the second measurement has been taken by a meter that is better accuracy, millimeters. So this is actually 123 milliamps. 123 milliamps. Right? So 123 milliamps. So although that is better accurate, you are adding that with a coarser number, this accurate number, where you didn't know what is happening with the second and the third decimal places. Right? So therefore we have to limit our result to the coarser most accuracy. Right? Which is, we know the factor details about the first decimal point only. So your result should be truncated there. First decimal. Right? Because at least one of your numbers are not accurate beyond that one. Right? Addition, subtraction, we follow that. Multiplication, division, we follow this. These are references. And that's it for today and for this week. So the tutorials are there. Sheets are there. So now it's your duty to do the pre-level, get prepared, and go through the tutorial as well. And be prepared. We will give you your kit and then get it. Right?